Hallo?
Good morning. My name is Elisabeth Dötzlofer-Ferry. I am Sales Assistant at Phil, and we would like to welcome you to our webinar, Accubot-based ultrasonic X-ray inspection and geometrical measurement systems. In the next 60 minutes, we will show you the highlights of these systems. Before we start, we will explain the tool, briefly introduce the company, the team, and then we start with the presentation. I would like to introduce our team before we start. Our specialist, Thomas Gramberger, will showcase today the highlights of our newest developments in the automated NDT and metrology for aerospace. Balthasar Fischer, the CEO and founder of XARION, will introduce his unique alternative for dry inspection, the so-called optical microphone. And we are happy to welcome Jakob Schekelja from GKN Munich, one of our customers who is using an industrialized NDT system based on the Accubot since 2018. We are pleased that our CEO, Andreas Vill, will be open the webinar. Our senior sales manager, Wolfgang Hase, will answer your questions in the background, and I am happy to lead you through the webinar today. Now, I give the floor to Andreas Vill.
Good morning, good afternoon, and good evening to all over the world. Welcome to our day's webinar of NDT and metrology for aerospace. My name is Andy Vill. I'm the CEO and owner of the company. I'm sorry for the little delay, and I wish you for this webinar 60 exciting minutes. I'm proud to welcome more than 150 experts of the NDT community from 19 different countries. And I'm proud to present you our latest developments and solutions in the field of Accubot metrology and testing, and our latest innovation in the field of cybernetics. So for you all over the world, all the best, and all the best for our day webinar.
Thank you, Andreas, for the introduction of the Phil company. During the repositioning of the camera, please kindly have a look on the overview about the unique system architecture. Thomas Gramberger will present the first application and kinematics independent approach for NDT in aerospace, which helps our customers to optimize their return of invest by utilizing the so-called multimodal concept, which allows to combine different kinds of NDT technology. Now I give the floor to Thomas Gramberger.
Hello everybody, my name is Thomas Gramberger and I'm working since 2009 at Phil. I have started my career as a software engineer, and since a few years I'm taking care about the NDT business together with my colleague Wolfgang Hase. Today we would like to present you the so-called first application and kinematic independent aerospace NDT approach powered by Phil Studio. What means that? I will show you in the next few minutes more in detail. We call this multimodality. Multimodality means that at the end, the customer and the operator of the system should not take care about which technology or which kinematic needs to be operated. At the end, for the user, the look and feel of the machine, how to operate the machine is always very similar. So we try to integrate as much different NDT processes and metrology process in our framework as possible and make it very convenient for the user to work with it. Today, we would like to show you several different applications, starting from ultrasonic, followed by X-ray inspection, and later I will show you the metrology process more in detail. Before closing the event, I will talk about the AccuBot system and our digital solutions, because Phil Studio is our digital framework for combining all these different technologies together. Okay, now let's start, and please follow me. Our plan is to start with the ultrasonic. Okay, let's start. The visible setup here is a typical setup of a dual robotic system, mainly for ultrasonic inspection. But as you can see later, we have included here the metrology application in a very light stage as well. The first robot has mounted a so-called metrology tool, which is actually a structured light camera, and the camera is acquiring 3D point clouds. We use this in the referencing mode to determine the position of the specimen inside the inspection area and to avoid any manual teaching processes. So robot 1 is working totally independent from robot 2. Robot 2 in this case is guiding a fork and is performing through transmission ultrasonic inspection. For simple 2D parts, through transmission inspection is even possible with only one robot, as you can see here. As soon as we have bigger parts with high curved surfaces, we might need to move to the dual robot setup. Okay, now I would like to go more in detail about our ultrasonic solution. The small red box, which is visible here, is our UT electronics. It's from our partner and supplier Force Technology from Denmark, and it provides 8 high dynamic single channel ultrasonic channels and is able to perform phased array inspection as well. For through transmission inspection, the single channels provide very high dynamics. So with 1 megahertz, we can reach up to 120 dB usable dynamic, and with 5 megahertz, it goes up to 115 dB, which is quite much, especially for high damping materials. Then we have a high linear resolution with acquisition of in 24 bits, and a highlight is even the integrated burst pulsar, which allows the through transmission inspection of highly damping materials. Another unique feature is the dual frequency inspection. As you can see in this test setup, here we are inspecting an AITM hysteresis test panel, and this setup provides a dual frequency setup, and that means we can inspect in 1 and 5 megahertz simultaneously in one scan. Especially for through transmission inspection, the unique and high inspection speed of up to 2 megahertz is quite impressive. This for reaching such high inspection speeds, even our maximum pulse repetition frequency of up to 4 kilohertz is mandatory. As soon as the UT acquisition has been done, the scan has finished, we need to move over to the evaluation of the UT data. And therefore, we are working with our partner Testia and their product NDT Kit UT, which was formerly known as Ultis. This tool provides sophisticated evaluation and reporting functionalities, and we are working with the NK3 format, which includes the full 3D data together with the acquired A-scan and UT data. For NDT data management on plant level, we are partnering with a company from the UK. They are called Chatsoft, and they provide sophisticated tools for managing NDT data on plant level. For UT inspection, we even provide phased array functionality. The highlight of the phased array board of this UT device is the conversion rate, the high conversion rate of up to 120 megahertz. This is especially interesting for thick solid materials in phased array inspection. And we can support up to transducers with up to 128 elements. What we have as well is our so-called flex change tool changer. I will explain it more in detail later. And with this flex change, we can easily, fully automatically exchange between different tools and applications. As you can see here, starting with this so-called narrow active tool. This is for through transmission inspection of very confined spaces. As you can see here, we have a small nozzle which can rotate. This is fully implemented in the kinematic structure of the cinemeric controller. This is a flat slider for phased array inspection of flat and slightly curved parts with 64 elements in this case. And we even have designed dedicated radius inspection tools for outer and inner radius inspection. And all these tools can fully exchange automatically. As we have talked about mainly the wet ultrasonic right now, we are even partnering with companies who supply the technology for air couple duty. In this case, I would like to mention our partner Sonotec and XARION, which delivers both very interesting technologies for dry inspection. Okay, now I would like to hand over to Elisabeth because we move to the next part of the machine.
So, Thomas is now moving to the next system, showing the X-ray and metrology application. In the meantime, you can read some more features of it.
Now we have moved to the next system, which is still based on our universal architecture, the high precision robot AccuBot, but here we are showing a different technology. It is X-ray inspection. In this case, the customer has decided to include an additional application to justify the investment for the X-ray robot. And in this case, it is the metrology application to perform high precision geometrical measurement of the part, contactless for sure. Now the robot is starting with the X-ray inspection. Here the system is equipped with a 130 kilovolt microfocus tube. The tube is right now not mounted because as we do not have any bunker here, we are not able to perform real radiation. But nevertheless, you can imagine the X-ray source on the right side of the fork here. So the robot is starting with the X-ray inspection. The X-ray trajectories have been generated by an offline programming and simulation system based on CATIA data. But something what is very innovative in this case is that we combine the digital data coming out from the simulation, the trajectories, with manual corrections done by the joystick, as commonly known from legacy systems, because today most of the X-ray systems are controlled only manually by joystick. Here we have a so-called assisted mode, because if you would like to inspect honeycomb areas, like here with this aluminum trailing edge, it is very important to be perpendicular to the aluminum core areas. As this perpendicularity cannot be granted due to some production tolerances, it is not sufficient to rely on the OLP data. So the operator can manually correct the OLP data, and all this acquired data will be fed back in the engineering loop and in the OLP system, and the system can learn by itself. So this is based on newest digitalization strategies, the whole process. As you can see here, there are no visible vibrations. So you immediately after moving to the next acquisition point, you have a sharp and crisp image generated by the digital detector. By the way, for the X-ray technology, we are working with our partner VigiConsult. Okay, now as soon as the X-ray procedure has been finished, the robot is automatically exchanging its end-of-arm tool to the metrology tool. As soon as the changing procedure has finished, I will explain more in detail about the metrology application. We have a small defect marker integrated in our flex change tool changer as well to highlight some regions of interest on the specimen. You can see this defect marker now. As soon as no tool is mounted, it is just a small pneumatic actuated defect marking tool based on an inkjet. Now the robot is picking up the metrology tool. So the metrology tool is basically equipped with two different sensors. One sensor is a 3D point cloud sensor based on structured light technology. And additionally, we have equipped the end-of-arm tool with a high resolution 2D sensor with 25 megapixels for a dedicated region of interest inspection. So basically, the procedure is like this. All the trajectories are programmed in the offline programming system based on dedicated visual inspection algorithms, because we need to guarantee some overlap between the acquisition points. And then as soon as the structured light sensor is acquiring 3D point clouds, we are just merging all these different point clouds together. So the whole set of point clouds will now be combined, meshed, and then we perform a comparison with the original 3D data. At the end, the customer gets a fully automated generated report about all the deviations and thresholds and so on. What is very important here is that we do not rely on photogrammetry technology here. We rely on the high positioning accuracy of our AccuBot system, which is unique, and therefore we can avoid relying on some specific features on the part to align the different acquisition points together. So we are not depending on any features and patterns on the part to align the different point clouds together. And as mentioned before, for example, for drill hole diameter inspection, we use our 25 megapixel 2D vision sensor. As you might see now, the blue light is the structured light which is being projected on the part, and the sensor is acquiring the 3D point cloud out of it. And a nice feature of the system is, after finishing all the processes, starting from X-ray and metrology, we merge all the results together using our Fill Studio, and then we generate a measuring report containing all the different results of X-ray and metrology and ROI inspection of the 2D camera together. Another interesting feature is our laser-based calibration, because some participants may ask why or how can we guarantee the accuracy of the robot during the operation. And therefore, we have decided to rely on a laser-based calibration system, and therefore we don't need a laser tracker stationary in the inspection cell, because we use the laser tracker for the initial calibration of the robot to reach the high accuracy of 0.1 millimeter absolute on the TCP. But then, as soon as the initial calibration has been finished, we can switch over, we can remove the tracker, we switch to this laser-based accuracy verification system, and with this system, the operator of the cell can verify the accuracy of the overall kinematics chain whenever he wants. So typically, before each shift start, the operator is just starting the verification procedure. It takes about 2 minutes, and then the operator gets a message whether the accuracy of the robot is still okay, and he can rely on the acquired data. Okay, now I would like to go back to Elisabeth.
Thank you, Thomas. Now I would like to hand over to Mr. Balthasar Fischer, CEO and founder of XARION Laser Acoustics.
Good morning, everybody. My name is Balthasar Fischer. In the next 5 to 10 minutes, I would like to present you yet another testing modality compatible with the fill system, with the fill ecosystem. My topic is laser excited acoustics. I'm the CEO of XARION Laser Acoustics. We're based in Vienna and developed this new ultrasonic inspection technology. So let me start with a brief note on our company. As mentioned, we are in a very close partnership with Phil. So we are a producer of a sensor, and this can be combined with the Phil robotics to allow for an additional inspection modality. Our company was founded in 2012. We have two main shareholders on board, which is Hans-Peter Porsche. He's a member of the Porsche family, and the laser company Trumpf, because our topic is obviously very laser related. As mentioned, we are based in Vienna, and we started as a startup company. Now we employ 31 individuals, is specialists in the field of laser physics, acoustic, electrical engineering mainly. So what is laser excited acoustics? We use a short laser pulse to generate a thermoacoustic shock wave on the sample, and then we use what we call an optical microphone to recapture the ultrasonic signal radiated from the sample. And obviously then the ultrasonic wave radiated from the sample will contain information on the defect, such as delamination inside the sample. So how come that a laser pulse is generating ultrasound? It's a very short laser pulse, and the spot where it hits the sample, there would be a little increase of temperature, and that leads to an expansion, and that produces a thermoacoustic, or in other words, ultrasonic shock wave. And this is how we generate the ultrasound. So there is a single-sided configuration shown here, where the laser excitation and the receiver are placed on the same side, and there is a through transmission setup, a TTU, where we would have excitation and optical microphone on opposite sides. I'd like to show two examples, two scan examples. This is a example of a CFRP honeycomb sandwich plate. You see a photo on the left-hand side and a scan image on the right-hand side, and there are a couple of reference defects. So obviously you can nicely see them in the scan image, and in terms of speed and resolution, the technology is, I would say, comparable to a squirter. However, the nice thing about it, it's completely contact-free, so no water, no gel, no liquid is used to generate the image. In terms of water management, it can be interesting because it might need less pre-treatment, especially if you deal with open core material, where you might have to close the surface for the water ingress. So this is an application where I guess it would make sense to refrain from a coupling fluid. I'd like to draw your attention to this little insert here. So this shows a zoom of the smallest defect. You nicely see the honeycomb core, the single pores. So we have a pitch of 3 millimeters, and centered in this insert, you see the smallest defect. The second example is detection of porosity in monolithic carbon fiber material. So if you acoustically ping on pores having a size of 1 millimeter or less, they tend to radiate an ultrasonic wave as a response. So our laser excitation is very broadband, and if we then use our optical microphone, which is frequency-wise very broadband as well, we can make visible the pores inside the material. So again, key is to have a broadband excitation and a broadband receiver, because depending on the size of the pores, the resonance frequency will be in the few hundred kilohertz range. So this shows a scan image. It's a regular C scan of a material containing pores, and I put some scale on it so you can see even pores smaller than 1 millimeter, clearly smaller than 1 millimeter can be shown. Also, it has to be noted that the size of the pore here does not directly correspond to the pore size, but the pores resonate in a specific frequency, and then in offline analysis, you can filter for the specific frequency, and you can make visible pores of a given size. Let me do a little bit of a comparison. If we compare laser excited acoustics to squirter, one thing you need to keep in mind is laser safety. So we need to take laser safety precautions. However, on the advantage side, it's a very small inspection head. If you look at the image there, it's a true transmission setup. It's a really tiny receiver head, so it's possible to go into complex geometries or confined spaces. The receiver is very robust against angular misalignment, so it's okay to have 10 or 20 degree misalignment. And obviously, as I mentioned, water is used for the ultrasonic inspection. If we compare it to traditional laser ultrasound, you might have heard there is something like traditional laser ultrasonics. There is a image here on the right-hand side showing a setup from Airbus. I believe it's from the 90s. I'd like to draw your attention to the size of the inspection head. If you compare that to that person standing down on the floor, you see it's a rather bulky setup. And also that box there, the laser generator, in the past, those used to be much bigger. So nowadays it's possible to have a rack-based unit at much lower cost and obviously much smaller size. Our setup is purely fiber-based. So the entire inspection head is shown on the left-hand side in the image. It contains the generation and the receiver of the ultrasound. Finally, I'd like to compare it to air-coupled ultrasonic testing. Our customer provided a reference scan to us and sent us the same plate for inspection in our lab. You see our lab on our result on the left-hand side. It's the same plate shown before. And on the right-hand side, a reference image obtained with a 400 kilohertz air-coupled test. And clearly there's a much better resolution. This is due to the very small active area of our optical microphone, which is less than 1 square millimeter. So that's why you can generate very sharp images. But it's not only the resolution, it's also the speed. We can have up to 5 kilohertz of pulse repetition frequency. So obviously it means high speed. And last but not least, a very high frequency bandwidth. So in one scan, you capture the entire frequency bandwidth between or expanding from 50 kilohertz up to 3 megahertz. So you don't have a center frequency, but you have really a broadband signal. And then after the scan, you can decide whether you want to apply a digital filter and look for a specific feature at a specific frequency. So it captures all at the same time. Let me close by summarizing briefly. It's a fiber-coupled sensor head based on laser excited acoustic. It's compatible to the Phil standard industrial solution. It's basically a plug and play setup which has been tested at the Phil facility. It well fits into the Phil robotics environment, and the AITM for the Airbus qualification is right now underway. So thank you very much for your attention.
Hello, my name is Jakob Scheckiner. I'm the head of quality assurance here at BKM Aerospace site Munich. We had in the past old ultrasonic equipment that was built 1986. Was modernized several times, but as such old equipment and modernization, it works for a while, but it's not reliable on the long term, even with modernization and upgrades. So we decided 2017 that we will go for a completely new equipment, but with a difficulty here, that the ultrasound is embedded middle in the production area and it should stay still here. So we didn't have the possibility to move with the new equipment to another area. So we decided to build this new equipment more or less parallel to the old equipment. It means we leave the old equipment here at the site where it is, built the first robot parallel to the old equipment. I've started with setups, with qualification and so on, and as soon as we have finished all of the work that is necessary for the aerospace business, we have decided to scrap the old equipment and use the Robot 1 for the production. So we didn't have any impact on the production during all of the build-up and qualification phase. After this old equipment was scrapped, we started with the build-up of Robot 2. This happened 2018. And then after it was finished, we also qualified the Robot 2 for all of the parts that we already qualified Robot 1. Why have we done this? Why have we purchased 2 robots? The main reason was we needed reliability here. We had in the past just one equipment, and during a breakdown, everything was down. We had a single point of failure, and the whole production was stopped. With 2 robots, we have the opportunity to further inspect, even if one robot is defect, just set up everything on the Robot 2 and vice versa. It was one of the reasons. Second thing was we have implemented 3 working areas. One in the middle where the robots can do cooperative work, and then on the both sides of the robots, on the outer sides, we have also the possibility to do further work. Also, with the safety system included, we are able to make a setup of parts in one area, and during this time, is the other section of the robot not affected. That means you can still inspect on the other side of the area further without disturbing the robot in his inspection. So we are far more flexible. Also, the technology of these robots have been improved. In the past, we used, of course, the state-of-the-art technology for this time with single channels, but meanwhile, we are on very fast phase array technology. In the past, we needed for one of our large parts in full sector about 100 minutes, and we are now down to 8 minutes for the same parts. This is a great improvement. There's of course a question, if you manage to do everything in the past with one machine and that slow time, now you have 2 machines actually and are far faster. Are they all actually utilize the whole machine? Do you have enough parts here to work? Yes, because we could go just down to 1 shift. From 3 shifts model, we are down to just 1 shift. We have reduced our personnel here because everything is quickly done. And second thing is you have very precise robots, and you can also utilize other inspection methods on the part. And in this case, we are using the robot not only for the ultrasound inspection. For example, the very direct plus of the robot was we are making the wall thickness of our parts also with the software included, in this case Altis. The data you are getting from the robot are already providing you some of the vital data for the wall thickness. Why not to use them? To increase the utilization time of the machine, it was planned to do the wall thickness and as well other applications. For example, you can install quite easily a laser scanner on it and scan geometrically your parts. Especially here, where we have 11 meters long parts, it is quite hard to inspect them per hand and scan them completely, so we decided to install a laser scanner where you can scan the complete surface of about 15 square meters in a very high resolution, and the engineering data generated from that are very valuable for our production. So the robots have extremely high utilization, and this is thanks to the very high flexibility of those. They are very accurate, and also they have the possibility to quite easily exchange the tools. Also, the software behind it is flexible. It doesn't need any additional interfaces. You can program just the trajectories, and it is running according to your wish, and everything else can be solved by the external software from the laser tracker, from the scanning equipment, and so on. To simplify the utilization of such a complex system, we have reduced the software to the nominal issues that the operators need. In this case, just scanning up the material number from the traveler or the work order and the serial number. We just do this data. It is possible to exactly say which program will be used, to exactly say in which safe location it will be safe, and everything else needed.
Now I would like to tell you more about our Acubot system. The Acubot is a high precision robot driven by a Siemens kinematic controller. Actually, to reach this extraordinary absolute positioning accuracies, we have applied secondary encoders to all the robotic joints. So we buy the robotic arm from Stäubli, which is our supplier. Stäubli delivers very reliable, precise, and waterproof kinematics. And then we combine this kinematics with the openness and the performance of the Siemens kinematic controller. And this gives us a lot of flexibility to extend the kinematics, to modify the kinematics, because as you see in one of the next scan lines, we have implemented the so-called active tool, which allows to add an additional servo motor or an additional axis in the tip of the robot on the end of arm tool, fully integrated in the kinematic chain of the robot. So in a few lines, you will see that the active tool will move to the next position. And until we reach this point, I would like to talk a little bit more about the high precision of the Acubot. We include these external encoders on all axes to eliminate and reduce the mechanical backlash of all the gears. Even thermal effects and wear effects of the gears are totally eliminated. And the final effect is that we reduce the repeatability of all the single joints drastically. Additionally to the external encoders, we implemented a real-time compensation based on a laser tracker. So for the initial calibration, we place the laser tracker in the inspection area, and the robot, the real robot, will be identified, the kinematics model of the real robot, because for sure the real robot will differ from the ideal nominal CAD model. And this calibration is in a later stage calculated in the real-time cycle of the kinematic controller to compensate all the geometrical deviations we are facing. Now you see the active tool has moved to another orientation, and the robots are continuing with the inspection in a new constellation. What you can see here is the inspection speed of 2 meters per second, which is quite impressive. Especially important here is that the trigger rate, the maximum pulse repetition frequency, is up to 4 kilohertz. And all these different tools you have seen before, the phased array tools, the X-ray tools, the metrology tools, they are fully automatically exchangeable with our flex change tool changing system. The flex change system is visible here as well. Okay, now I would like to move and to go more in detail about our digital solutions. Just follow me. What you see here is our so-called Fill Studio, our application and kinematics independent framework for NDT inspection systems. We have here integrated several tools specially designed for the dedicated process. Let's say for ultrasonic inspection, we have dedicated path planning algorithms. We have the same for X-ray inspection and for metrology inspection. So we try to combine all these different applications in one tool. So at the end, for the operator, it does not matter whether he's operating a robotic system or a gantry-based system or any other special kinematics. And in the same way, we try to implement different applications. So for the operator, the look and feel in the software is always the same, no matter whether he's operating an ultrasonic system, an X-ray system, or a metrology-based system. Our Fill Studio supports even a huge variety of state-of-the-art protocols to communicate with ERP systems on plant level, based on MQTT, OPC, UA, and all these new standards, which are used for the new IoT and Industry 4.0 technologies. What we have as well is a fully implemented digital twin based on VNCK. Here, this is another feature where we utilize the performance and the power and the flexibility of the numeric controller. We have integrated the digital twin to perform cycle time analysis, collision avoidance, singularity avoidance in parallel to a running inspection. So this is quite convenient for all users to utilize to a maximum machine utilization. For complex 3D geometries, we are partnering with AC&D from UK. With their product, eHub NDI, we generate our scanning trajectories, especially designed for ultrasonic, on complex 3D shapes. As you can see here, this is a winglet, and we can generate the scan paths with this tool on any complex surfaces. We have even implemented our active tool in this offline programming and simulation environment, and then we can easily program, simulate all the scanning trajectories in parallel to the running system. So no need anymore to interrupt a running inspection on the real system. Our Field Studio, I would like to show you some nice feature, because in the beginning of the webinar, you have seen that we have worked with the metrology feature. The Robot 1 has just acquired a point cloud of the specimen, which has been inspected by Robot 2. And here you see the result of the point cloud. Here you can imagine the AITM reference panel. If you are an UT expert, you may recognize that this is the AITM reference panel, and we can easily adjust our reference to this acquisition point cloud, and we can immediately start the scan without any manual intervention or manual teaching. So metrology is fully implemented in Field Studio as well. Another nice feature is the multi-station capability. Just imagine the two robots are working independently from each other. Robot 1 is doing a phased array inspection in work zone 1, for instance. Robot 2 is performing phased array inspection in work zone 3, absolutely independent. Each robot has his own Field Studio instance to be controlled by Field Studio. But even if Robot 2 is still doing an independent job, you can already start here through transmission inspection with two robots in the middle area, in the middle of the three inspection areas. And Field Studio is automatically coordinating the resources between each other. So as soon as Robot 2 has finished its job, Robot 2 will be assigned to Field Studio of Robot 1, and they are doing their automated cooperating job. Okay, I hope you have enjoyed this presentation, and we were able to give you an insight about our latest developments in automated NDT and metrology for the aerospace industry. And we are looking forward to discuss with you your personal requirements, and see you soon.
Thank you, Thomas. Now we are happy to answer the most frequently asked questions. So let me hand you over to Mr. Wolfgang Hase.
Hello from Germany. Due to the current situation, I'm not in the company and working from home. We did not receive too many questions. Most questions were related to XARION, which we answered online. Another question was regarding the phased array. Has the phased array electronics, the TTU single channel implemented, or is it a separate additional extension? No, it is completely incorporated. So we have the 64 channel phased array system, which is already equipped with this 4 to 8 channel TTU equipment for high dynamic TTU inspection. Then also, if the burst pulsar is based in the basic scope of supply, yes, the burst pulsar is in the basic scope of supply. And what about the burst pulsar? Where would you use it? The burst pulsar generates up to 4 full cycles of 200 volt transmitting signals. This boosts up your transmitting signal in a range of 15 dB, so comparable with a standard rectangular pulsar. You boost your signal to an energy level of 600 to 800 volts. But as the crystal is only getting the 200 volt, you do not damage the crystal over a long time, so it has a long durability. Yeah, these were the questions we had. Thank you very much and wish you a nice day.
So, thank you, Wolfgang. Additionally to this webinar, we will send you an email with all important information till the end of the week. So you will receive the link to today's recording, important product details, and contact addresses. If you would like to learn more about Phil, please visit our homepage or follow us on the social media channels. Our experts are always available to answer any open questions. Now, we wish you a pleasant day and look forward to hearing from you soon. If you stay here for a short time, you will see some more pictures of Phil to get an insight into the company. Goodbye.